So in this lecture we're going to talk about the fundamental theorem of calculus. As the name suggests, this is the most important theorem of the course, and it's actually one of the most important discoveries of mankind. So if you remember in the previous lectures, we defined the integral, and when we defined the integral, we did not use the notion of a derivative at all. The integral is not defined in terms of derivatives at all. So the fundamental theorem of calculus is where we bring forth the relationship between integrals and derivatives. So this is a kind of an impressive result because, well, we're thinking about integrals in terms of areas. What does that have to do with derivatives and slopes of tangent lines? So I'm going to try to explain that in just a moment, but I want you to really take a moment to reflect upon the fact that the definition of integral was in terms of these Riemann sums and didn't have anything to do with derivatives. So it might be surprising that there is a relationship between integration and derivatives. So if you think back to, say, like high school calculus, a lot of the times, or even your Calculus 1 course, a lot of the time, the integral is defined in terms of an antiderivative. And so in that case, you get used to thinking about the two, an integral and an antiderivative, being synonymous, but it's actually not the definition of an integral. It is a very deep and important result that integration and differentiation are reverse processes of each other. So we're going to state the fundamental theorem of calculus. So let's say I have a function defined on the interval AB, and I'm assuming it's continuous, and then I define capital F. So capital F of x is the integral from a to x of f of t dt. So here I'm using t and dt, but you know those are dummy variables. The name of the variable here doesn't matter. But this capital F, the variable of my function, isn't this variable over here. The thing that's varying is the endpoint x. Okay? So the fundamental theorem of calculus part 1 says that if I take my little f and then define a capital F in terms of the little f using an integral, then this capital F is an antiderivative of a little f in the sense that the derivative of capital F is little f. Okay? That's the fundamental theorem of part 1, and that's the important part, although not the practical part. This is the one that gives me the relationship that says integration and derivation are inverse processes of each other, because if I take little f and integrate and then take a derivative, I just get little f again. So I integrated and took a derivative, and those two things cancel each other out. That's the importance of part 1. So part 2 is the part that we use all the time in Calculus 1. So if I have a little f and have any antiderivative, capital G, then the integral of little f on AB is just g of b minus g of a. This is what we see all the time when we're doing calculus and we actually want to evaluate an integral. This is how we do it, right? This is almost, and a lot of times in math classes that are not as focused on the theory as we are, sometimes this is taken to be the definition of the integral, but it's not. It's a very deep fact that I can evaluate an integral using antiderivatives. Right? So take little f, find an antiderivative, plug in b and a, and subtract. That's how we evaluated all of our definite integrals in Calculus 2, almost all of them. So I'm going to give the idea, and then we're going to give the proof. So the idea is that actually turns out to be very simple. So I want to look at the rate of change. Right? So I have this function capital F, and I want to know f prime. It's the rate of change. So what I'm going to do is I'm going to go from x to x plus h. I'm going to see what is the change in capital F and divide it by h, and that'll give me the rate of change of capital F. So our integrals are not defined in terms of areas, but they should be interpreted that way, at least as net areas, because the integrals can be negative. Right? So when I think about it this way, the capital F of x plus h is the integral from a to x plus h of little f. Right? So this is a graph of my function little f. Capital F of x plus h is the integral from a to x plus h, which means that includes the black area and the blue area. Right? So black plus blue is that f of x plus h. F of x is the integral from a to x. Right? So that's just the black part. So this numerator here is the blue part plus the black part minus the black part, which just leaves me with the blue part. And the denominator is h. And what I want to point out is that if h is very small, this blue part is almost a rectangle, and the height of the rectangle is about f of x. So the area of the blue part, which is what the numerator is here, is approximately the area of this rectangle. The width of this rectangle is h, the height is approximately f of x, So the area of the blue part is approximately f of x times h over h. H is canceled and I get f of x. Okay. So if I think about increasing this region whose area I'm taking and then figuring out what's the rate of change, it's just this blue part. Okay. And the fact that the height of the blue part is about the value of the function f is the reason behind this theorem. Okay. So now we're going to do part of the proof. When I say part of the proof, I mean I'm going to tell you what parts I'm leaving out. Okay, so I'm going to compute capital F prime for x that's between a and b. If I want to do it when x is equal to a, then I have to do a limit from the right. Okay, so I'm going to look at this limit. If x is equal to a, then I have to look at specifically a limit from the right. And if x is equal to b, then I have to do a limit from the left. You have to make those adjustments just for the sake of not having to write out 3 different cases that look very similar. I'm just going to do the case where a is between. However, since I'm doing the limit, it needs to be the 2-sided limit, but I'm only going to show one side, and I'm going to leave it to you to figure out how to do the other side. So here I'm going to do it for positive h. Right? So I want to take the limit of this as h goes to 0. Here I'm going to take the limit of h goes to 0 from the right, and you have to figure out how to do it from the left. Okay? So this f of x plus h, by definition, is the integral from a to x plus h of the function. This capital F of x is the integral from a to x of the function, and it's all over h. Now, by the properties of integrals that we talked about in the previous lectures, this integral from a to x plus h is the integral from a to x plus integral from x to x plus h. Now, this is something you have to worry about if h is negative. So here we're going to do the positive h case. If h is negative, then x plus h is not in between a and x. You have to think about that a little bit and figure out if that causes a problem with the step or not. Okay, so I got left out all this paragraph up here, so let me go remind us what this paragraph is. So fix a positive epsilon, and because little f is continuous, I can fix a positive delta such that for any x and y, whose distance is less than delta, distance from x to y is less than delta, then the distance from f of x to f of y is less than epsilon. I can do that because little f is continuous. And now fix an x between a and b and fix a positive h which is less than delta. And because I need the little f to be defined in between x and x plus h, I'm also going to assume that x plus h is less than beta. So what I've done here is I have a, and I have b, and I have x somewhere in between. And now I want so I want to do x plus h, or x plus delta, x minus delta, and I want to be guaranteed to choose delta small enough that this, if I take an x plus h inside this interval, it doesn't go outside of the AB interval because then the function's not defined there. But so all I'm doing is saying that delta and h should be small enough that x plus h, x minus h stay inside the interval. I guess I should have said, since I'm just doing on the right, I only need x plus h to stay inside the interval. If I was doing the limit from the left, I would need x minus h to not go to the other side of a. In any case, this integral, I split it up, a to x plus x to x plus h. This part will cancel. Okay? And now I get just integral from x to x plus h of f of t dt over h. Okay? So this quantity reduces to this, just the integral from x to x plus h. F of t dt over h. Right? So I'm going to use this fact on the next page. I'm going to continue. Okay? So for each t between x and x plus h, since h is less than delta, the distance from t to x is less than the distance from less than or equal to the distance from x to x plus h, which is h, which is less than delta. So if t is in between x and x plus h, then the distance from t to x is less than delta, which by our choice of delta means the distance from f of t to f of x is less than epsilon. So now, using what we proved on the previous page, this fraction is equal to this this fraction. So I'm going to have f of x plus h minus f of x over h. So this entire fraction here I replace with this fraction from the previous page, and I factor out a 1 over h. Okay, so I replace this with what it's equal to from the previous page, and I get a common denominator of h over here. Right, so let me do that here. And then I'm going to factor out the 1 over h. And now this integral, or this h times f of x, is the same as the integral from x to x plus h of f of x. Here, notice that this is f of x dt. In this integral, x is a constant, so I'm integrating the constant value, f of x, over the integral from x to x plus h. Okay? Really what that means is, this integral is the area of this actual rectangle. So here, this function is f of t, this value is f of x, and x is constant, so it's not changing. So I'm integrating this flat value from x to x plus h, and I just get the area of that rectangle, right? So that's what I did here. So the idea here is, here it's f of t dt, here it's f of x dt, and x is a constant. So this is the integral of a constant value f of x, right? So now it's the integral from x to x plus h of, it's the same end points on both integrals, so I can bring it together as one function. I can squeeze the inequalities to the inside. Here I'm using the fact that h is positive. Right? So I'm using a lot of the facts that we proved in the previous lecture, including that x is less than x plus h to squeeze it inside, squeeze the absolute values inside. And now, by this line up here, f of t minus f of x is less than epsilon. So this thing is less than epsilon, so I can replace the whole thing with epsilon and use our fact 5 from the previous lecture. If I integrate a function whose absolute value is less than c, then the integral of the function is less than or equal to c times the length of the interval, which is what I'm using here. The length of this interval from x to x plus h is h. The function has absolute value less than epsilon, so the integral is less than epsilon times the length of the interval, and the 1 over h on the outside is going to cancel with this, and I get epsilon. So this, let me go back to the uncommon denominator. So if h is small enough, this is less than epsilon, which means the limit of this as h goes to 0 is this. And that's the end of the proof of part A. Well, I proved the limit from the right. You proved the limit from the left. So now we move on to part B. Part B is the practically important part. So by the mean value theorem, so recall what part B said. So here I defined capital F in a specific way, and I proved that capital F is an antiderivative of little f. So the derivative of capital F is little f. What part B says, if g is any function whose derivative is equal to little f, then this integral is g of b minus g of a. So here I gave a specific function whose derivative is little f, and here I'm saying if g is any function whose derivative is little f, then I can evaluate this integral by taking this difference. We're going to prove that now. So remember what we proved about the mean value theorem. If I have two functions whose derivatives are equal, then one function is just a constant plus the other one. Okay? So capital F prime is little f, or capital F is defined in part A of the fundamental theorem. And then by hypothesis of part B, capital G prime is little f, so capital F prime and capital G prime are the same. That means capital F, capital G are just different by some constant. And then the integral from a to b f of x dx is the integral from a to b f of x dx minus the integral from a to a. The integral from a to a of any function is 0. Okay? This is f of b. This is capital F of b and capital F of a. Capital F of b is capital G of b plus this constant. Capital F of a is capital G of a plus this constant. The constants c cancel. And we're done. And that's the fundamental theorem of calculus.